Hi folks, welcome to the Intro to Homotopy Type Theory video lecture series. In this lecture we're going to be discussing Martin-Löf Type Theory, which is the basic framework that Homotopy Type Theory is built out of. The question I want to answer with this lecture is, what is Martin-Löf Type Theory? And here's what our answer is going to be. Martin-Löf Type Theory consists of a formal language and a deductive system, which is structured somewhat like a typed programming language. And we'll see that Martin-Löf Type Theory is expressive enough to encode a wide swath of mathematics. In particular, we're going to understand MLTT as expressing both the topology of higher dimensional spaces and also a system of higher order intuitionistic logic. Lots of fancy words there, all of which I'll carefully define and explore over the course of this lecture series. My goal for this lecture is threefold. First of all, I want to give you a sense of what all this means. What's a formal language? What's a deductive system? What's a higher dimensional space? Second, I want to start defining the key mechanisms of Martin-Löf Type Theory, and argue along the way that it's everything I'm claiming it is. I say start defining because it'll take a couple lectures to fully describe the system. We'll get the basics out of the way here, but there are a few parts of MLTT, namely dependent types, inductive types, and identity types, which warrant their own separate lectures. The latter topic, identity types, will be the jumping off point for us to start doing homotopy type theory in earnest. And finally, my third goal for this lecture is to start getting our hands dirty with this type theory. MLTT is not just a thing we study, but it's a system we work with and a system we work in. It's important that we gain some experience actually using it. Let's start with formal languages. Mathematics, like basically all human endeavors, is made possible by written communication. Mathematicians make use of written language to convey their work to other mathematicians, and arguably the main activity that constitutes doing mathematics is producing written mathematical arguments or proofs. Now, for the most part, mathematicians communicate in a specialized variant of their natural language. For example, a proof might be written in English, just with a lot of specialized vocabulary, added symbols, and certain conventions. Such proofs we call informal proofs. Informal here doesn't mean that the proof is vague or unrigorous. It just means that it's written for a human reader. If you read a mathematics textbook or research paper, you'll find that the author relies on the fact that you, their reader, are a human person who's competent in the relevant branch of math. In order to make their proofs readable, and perhaps even enjoyable to read, they'll skip over small details, they'll assume familiarity with certain proof techniques, and they'll appeal to your intuitions. And, as mentioned, the proof is written in some human language. In order to make any sense of it, you'll definitely need to know what words like if and not mean. It's this assumed background that we're referring to as informal. But there's a problem with informal proofs. Suppose a mathematician announced that they had a proof of a result, but their proof is 500 pages of really complex reasoning. In order to verify that the proof is correct and contains no errors, it could take thousands of hours of work by highly trained specialists. And even they might not be able to catch a subtle but fatal flaw in the proof, or they might find themselves unable to say confidently that the proof is correct. And here the informal nature of proofs comes back to bite us. Since this proof was written by and for highly trained humans, there's no procedure for determining whether it's right or not. A proof can end up in a kind of epistemic purgatory, where it isn't definitely refuted or accepted. This isn't a hypothetical issue, by the way. This kind of thing has happened. Enter formal languages. A formal language is a precisely defined syntax for making statements about whatever it is we're studying. With a formal language, it is exactly and unambiguously specified what the meaningful phrases of the language are. The English language, for example, is not a formal language. You could not write down a rule or a computer program to define exactly what constitutes a meaningful English phrase. Martin-Löf Type Theory and Homotopy Type Theory, on the other hand, will turn out to satisfy this requirement. If we have a formal language expressive enough to capture all the mathematical structure we're interested in, which I'll say more about in a minute, then we can go on to define a deductive system, which is a mechanism that allows us to prove statements in this language. A deductive system will consist of a set of rules for constructing formal proofs. A formal language equipped with a deductive system is often called a formal system. So how does this address the problem with informal proofs? Well, if we've designed our formal system well, this system should have two properties. First, for any informal proof we write, there should be a way to formalize it, yielding a formal proof, i.e. a proof conducted in the formal language according to the rules of the deductive system. Designing a formal deductive system which can capture all the different kinds of reasoning possible in an informal proof is incredibly hard, and it's there that the true power of homotopy type theory lies. The second property we want is that we can program a computer to read any formal proof and verify whether it obeys the specification of a deductive system. This is precisely what couldn't be done for informal proofs, but for formal proofs it's possible. Because we made it absolutely precise and explicit what counts as a valid phrase in our formal language and what constitutes a proof in our deductive system, we're able to write a computer program that reads through the formal proof and checks that everything is correct. So if a mathematician writes her proof in a suitable deductive system, then it's much easier to check her work, no matter how long it is. It requires a computer, not a team of experts. It requires minutes or hours, not years. It will definitely come to a conclusion, not possibly be left open, and the computer will be able to patiently follow long arguments without losing track and making mistakes. It is for these reasons that it is becoming more common in mathematics to accompany one's informal proofs with a full formalization, a practice which homotopy type theory is designed to facilitate. So let's start to see how Martin-Löf type theory is defined. At the beginning, I said that MLTT has the form of a typed programming language, an assertion which I now would like to explain. A feature common to most programming languages is the formation of terms. Terms are syntactically valid strings of characters in the programming language whose value can be evaluated or calculated. For instance, in this pseudocode, b equals 4 or b equals 5 is what I'm calling a term, whose value in this case is false, because b is neither 4 nor 5. Many programming languages, furthermore, are typed programming languages. In a typed programming language, each term has a type, constraining what kinds of values it can have. For instance, b equals 4 or b equals 5 is a term of the type of Booleans, which has exactly two values, true and false. A typical typed programming language will have a bunch of different types, along with rules for uniquely determining the type of a given term, and rules for what type of term is required for the different constructs of the language. For instance, this if-then-else structure needs a Boolean term after the if, called the condition, because this if-then-else construct is supposed to do thing 1 if the value of the condition is true, and do thing 2 if the condition is false. It would be nonsense to write if 3 plus 5 do thing 1, else do thing 2, or if purple, then do thing 1, else thing 2, because 3 plus 5 and purple are not of the type Boolean. A typed programming language forbids such absurdities. MLTT is going to mimic this structure. The basic building block of MLTT are judgments, which are the assertions of basic facts in the language. There are four kinds of judgments in MLTT, and the first is called a typing judgment. Later on, we'll carefully develop what the terms and the types of MLTT are, but like in our programming example, each valid term is a term of some type. This is the kind of thing we'll be able to say in the language of MLTT, and we'll write it like this. If x is a term and t is a type, then x:t is the judgment that x is a term of type t. The second kind of judgment we'll introduce is that of judgmental equality of terms. If I have two terms, x and x prime, which are both of the same type t, then one thing I can express in MLTT is the equality of x and x prime, which we'll write like this. This judgment asserts that x and x prime are actually the same term. We'll cover the other two kinds of judgments in a minute, but for now we have these: typing judgments to express the relationship between a term and its type, and judgmental equality of terms to be able to say that two terms are in fact the same. These are really simple ingredients, but it turns out we can do a lot with them. So now let's discuss how we're going to interpret these judgments. As I indicated earlier, our ultimate interest is in developing a formal language rich enough to express the reasoning done in informal mathematics. In order for MLTT and later HoTT to fill that role, we need to say how we're interpreting the language of MLTT as talking about mathematical structure. Going back to this picture, what we want to do is understand the judgments of the MLTT language as statements about some mathematical structures. If this interpretation is sound, then any formal proof we conduct in the deductive system of MLTT will come out as true if interpreted as a claim about these mathematical structures. If so, then MLTT is a suitable system for formalizing informal proofs about these mathematical structures. In fact, there are two interpretations we'll apply to the language of MLTT. The first is what I'll call the homotopy interpretation, or the types as spaces interpretation. Homotopy type theory draws heavily from the mathematical discipline of algebraic topology, specifically the branch known as homotopy theory. In homotopy theory, the main objects of study are known as spaces. I won't formally define what a space is, but we'll generally think of spaces as regions of space or blobs existing in space. I'll usually draw low-dimensional examples, but this is merely out of artistic limitation. Spaces can exist in 3 and 4 and 5 and however many dimensions. One of the key reasons we want a formal language to talk about spaces is because informally reasoning and communicating about hyperdimensional objects is really hard to do effectively, which only exacerbates the aforementioned issues with verifying informal proofs. So we'll interpret the types of MLTT as referring to spaces. The terms of a type will then be understood as referring to points of the corresponding space. So under this interpretation, the judgment x is of type T says that x is a point located in the space T. If T, for example, is a line interval, which is a simple example of a space, then a point of T is some point along that interval. If T is a surface, then a point of T is a point along that surface. If T is some kind of volume, then a point of T is any point contained in that volume, and so on. Judgmentally equal terms, then, are understood as referring to the same point of the space. If x dot equals x prime, then x and x prime are the same point of the space T. So, in summary, under this homotopy interpretation, types are spaces and terms are points. The second interpretation is the types as propositions interpretation, often known as the Curry-Howard interpretation. Under this interpretation, the types are understood as propositions. The idea of a proposition comes from mathematical logic. A proposition is the kind of thing which can either hold or not. A proposition either is the case or is not the case. It rained last night is a proposition. Either it did rain or it did not. Mathematical logic concerns itself with different ways propositions can be combined and worked with, and this interpretation will allow us to express that reasoning in the formal framework of Martin-Löf Type Theory. So we'll understand the types to be propositions, and then the terms of a given type will be understood as witnesses to that proposition. If I see water collected in the rain gauge, then this tells me that it did indeed rain last night. The water serves as a witness to the truth of the proposition, it rained last night. So, if W is of type P, that means that W witnesses the truth of P, considered as a proposition. A type in MLTT is called inhabited if there exists a term of that type. We'll understand inhabited types as true propositions since there exists a witness to their truth. An uninhabited type, a type T such that there is no term of that type, will then stand for a false proposition because there's no witness to its truth. Judgmental equality, then, is just equality of witnesses. If W and W prime both witness P, then W is judgmentally equal to W prime means that they are actually the same witness. The main reason we're interested in equality of witnesses is so that we can study the possibility of multiple distinct witnesses to the same proposition. Now, some authors refer to witnesses as proofs, although I'm going to generally avoid that terminology just for clarity. But I mention it because there's a notion generally called proof relevance. A logic is proof relevant when it allows for distinct witnesses to the same proposition. Homotopy type theory is particularly notable for its very sophisticated notion of proof relevance, as we'll see moving forward. One final note about this logic: it's what's called an intuitionistic logic. Briefly, intuitionistic means that this logic denies a classical law of logic called the law of the excluded middle. This comes with some advantages and some disadvantages, but as we'll study more later, the law of the excluded middle is incompatible with our homotopy interpretation for most of the spaces we're interested in. Once we have the machinery of homotopy type theory in place, we'll be able to find circumstances where excluded middle fails. So, in summary, under this interpretation, types are propositions and terms are witnesses. So this is our situation. We've explored what a formal language is and what a deductive system is, and we've seen a tiny bit of what makes up the formal language of MLTT. In particular, we learned that MLTT, like typed programming languages, has terms and types, and we've seen how to understand these as either points and spaces or as witnesses and propositions. There's a couple benefits to using the same formal language with multiple interpretations, namely that it allows us to connect these interpretations. As we go along, we'll notice phenomena in the world of points and spaces which seem to have analogs in the world of witnesses and propositions, and it will prove useful for studying this analogy to express it in the language of MLTT. The other thing we're able to do is transpose concepts. We can take an operation which is commonly done on spaces, express it in MLTT, and then ask what does it mean when interpreted as talking about witnesses and propositions, or vice versa. Or we can take common type theoretic operations that are native to MLTT and see how they come out in either interpretation. So our next task will be to really dive into MLTT, develop all the features of the language, and specify how the deductive system works. Along the way, we'll see how these interpretations guide and motivate our choices, and provide critical intuition for the development of Martin-Löf Type Theory.